So far in this chapter, we've talked about standard deviation and variance, and so we're going to continue our discussion on the spread of normal data sets and the rules thereof in chapter 3.2. This is part 2 of that. So our objectives in this particular section is to use the empirical rule to summarize data that are unimodal and approximately symmetric, bell-shaped essentially. And we're also going to look at Chebyshev's inequality to describe a data set. And finally, we're going to compute something called the coefficient of variation. So before we get to discuss the empirical rule, I want to chat a little bit about the bell-shaped curve, first of all. The bell-shaped curve essentially looks like an actual bell. It peaks here at the center, and it has kind of a symmetrical spread. So many histograms that have a single mode near the center of the data and are approximately symmetric, such as the histogram that are below, is referred to as bell-shaped. And in some cases, we consider it approximately normal in future chapters. We will note that the empirical rule only works for normally distributed data distributions like the bell-shaped curve. So the empirical rule says basically the following. Given a bell-shaped curve, that 68% of the data are within one standard deviation of the mean. So that means that 68% of the data, that's not a percentile, which we're going to talk about later. It is the percentage of data within one standard deviation of the mean. For two standard deviations of the mean, 95% of the data is within those two standard deviations. This is going to become an important factor when we're looking at data that is somewhat skewed. And finally, almost all, in fact 99.7% of the data, are within three standard deviations of the mean under a normal curve. So we're going to use these factors in looking at the distribution of data in our data sets and to find extreme values if they're beyond certainly 2 and 3 standard deviations from the mean. Well, data is not always normally distributed, and we kind of want to know what's the percentage of data that we would find if the data set is not somewhat normally distributed. So in this case, we use something called Chebyshev's inequality. For any quantitative variable for any data set that's not bell-shaped distribution, the following rules apply, and this is called the Chebyshev's theorem. So essentially, the proportion of data that is within k standard deviations of the mean is at least 1 minus 1 over k squared percent of being within that portion of the mean. So in specifically, we let k equal 2 or 3, and we get the following information. For k equal 2 standard deviations from the mean, at least 3/4 of the data, or 75% of the data, are within 2 standard deviations of the mean. For k equals 3, at least 8/9 or 88.9% of the data is within 3 standard deviations of the mean. And so the way we calculate it for k is equal to 2, we would get 1 over 2 squared, which is equal to 1 minus 1/4, and 1 minus 1/4 is equal to 3/4. So you get the idea of how Chebyshev's inequality works. So here are two examples using the empirical or Chebyshev's rules. So we'll use the empirical rule first. So we'll look at the empirical rule first. Example, records at a hospital show that a certain surgical procedure takes an average of 162.8 minutes with a standard deviation of 4.9 minutes. Assuming that the data is approximately bell-shaped, that's an important factor, between what two values will about 95% of the data fall. So we calculate a lower bound and an upper bound, right? Our lower bound is the mean minus 2 standard deviations. So in this case, it is 162.8 minus 2 times 4.9, which gives us 153. And the upper bound is the mean, which is 162.8 plus 2 times 4.9, which is 9.8, and we get 172.6. So the way we represent this is an interval form. If you remember your math 1310, in interval form we have in interval form we have 153 to 172.6. So now we're going to take a look at Chebyshev's rule. The example here is a public health study. For systolic blood pressure was measured for a large group of people. The mean was 120. The standard deviation was 10. What information does Chebyshev's inequality provide about these data? Well, for 75% of the patients, the study is approximately between their blood pressure for systolic is between 100 and 140. And the reason we get that is when k is equal to 2, we multiply it by the standard deviation, which would give us 20, and we would add it to 20, which would give us 140, and we would subtract it from 20 to give us 100. And so for 89% of the data, certainly the study found that for systolic blood pressure in this study, the systolic blood pressure is between 90 and 150. And again, we calculate that by multiplying 3 times 10, which is the standard deviation, and adding it and subtracting it to the mean value of 120. Well, the coefficient of variation is somewhat a measurement of risk. It can be used in financial ideas about risk. And what it describes is how large the standard deviation is relative to its mean. And so it can be used to compare different data sets in the relative value of the spread measure relative to its mean value. So the formula for the coefficient of variation is called CV, and it's equal to the standard deviation divided by its mean value. Again, it's often used in financial data to compare data sets, to compare more risk versus less risk of different investments. But the example that we have here is to look at an example of the National Weather Service records show that over a 30-year period, the annual precipitation in Atlanta, Georgia, had a mean of 49.8 inches with a standard deviation of 7.6 inches. And the annual temperature had a mean of 62.2 degrees Fahrenheit with a standard deviation of 1.3 degrees. So we want to compute the coefficient of variation for both rain, precipitation, and for temperature, and which has a greater spread relative to its mean. And when we did the calculations for both, we see that rain has a CV of 0.153 and the temperature CV is 0.021. So in this conclusion is the rain amounts in Atlanta, Georgia appear to have more relative variation than its temperature. This concludes our chapter 3.2 on variation and spread. We will continue on in section 3.3 on learning about percentiles and box plots.